We have always heard it that radioactive decay is random. But the question is it really random? So, what if I told you that it is a predictable randomness or looks random, but it's not the chaos? It's mathematically organized randomness. Statistically, you can find a pattern. Today, we will dive into heart of radioactive decay, not through theory, but through simulation. We will watch atoms decay one by Monte Carlo methods and then compare it with the famous exponential decay curve and find out what's random and what's not. You have to understand here that we simulate radioactive decay not by solving math equation, not by assuming exponential decay curve, but by randomness of the nature, by Monte Carlo simulation. So along with the Monte Carlo simulation, we will also plot the mathematical solution of radioactive decay, that is exponential decay formula, and then we will check our simulation results satisfies this exponential behavior or not. So radioactive substances are made of atoms with unstable nucleus. You can think of nucleus as the core of the atom where protons and neutrons are tightly packed. But in radioactive atoms, the nucleus is not stable. It contains too much energy or an imbalance, in other words, imbalance in number of protons and neutrons, which makes the atom want to change itself into a something more stable. So every particle has a random chance to decay at each step. Okay. And we simulate this using random numbers. So each unstable nucleus will decay exponentially. That means it does not follow a fixed schedule. We cannot predict exactly when a particular atom will decay. It's random process at the level of individual atoms. But the interesting part is even though a single atom behaves randomly, a large group of atoms follow very predictable behavior. Or in other words, you can't say which atom will decay next. But statistically, a fixed percentage of atom will decay in a certain amount of time. As each has a fixed probability of decaying per unit time, this probability is quantified by a parameter called decay constant, denoted as lambda. So it's like if we start with 1,000 radioactive atoms, not all of them will decay at once. Instead, some will decay at each time step depending on their probability. That means we can predict the amount of atoms or percentage of atoms which will decay. As already told, we will use Monte Carlo method to simulate the radioactive decay. But the question is why Monte Carlo? So the Monte Carlo method doesn't try to solve equation analytically, or in other words, mathematically through equation. Instead, it uses randomness or random sampling to simulate physical process, just like our nature does with us. Like we are going to simulate radioactive decay by flipping virtual coins for each particle. In this code, after simulation, we have also plotted the mathematical solution based on the exponential decay formula and analyzed both of the results. But before diving into the code, you have to understand, or we have to understand these steps, the logics I have used in this code. So first is we start with 1,000 radioactive nucleus or 10,000. We have to fix a n0 at a time t equal to 0 or the initial number of radioactive atoms. Then we will give a value of lambda. So for an example, lambda is equal to 0.1, meaning each particle has a 10% chance to decay in each time step. Next step, the decay equal to np dot zeros and in bracket steps. So after decaying randomly, we create an empty array to store the number of atoms remaining at each time step. So here we are going to use for loop for our time loop. Next, the interesting part comes np.sum and np.random library. So this is the best part. This is the Monte Carlo part. Here, what happens? So first we generate in random numbers between 0 to 1. For each random number, we check if it is less than 0.1 or not. Okay, because we set our lambda values is 0.1, so that's why we are going to check that if it is less than 0.1 or not. So if yes, the atom has decayed in this time step, and we count how many such decays occur using np.sum. So basically, we are simulating each atom individually and asking that individual atom, will you decay right now based on the probability? So this is the basic logic. Okay. Next we subtract the number of decayed atoms from the total. This gives us the remaining atoms at this step. So let's dive into Python. Okay, so first thing first, let's change it to radioactive decay by Monte Carlo simulation. Okay, then now I am importing two libraries. One is NumPy, import NumPy as np, and another one is matplotlib, import matplotlib for plotting as plt. Okay, so now first we will put a random seed. So np dot random dot seed for reproducibility 0. Then put initial parameters, for example n0 equal to 1000. Let's say 1000 initial number of radioactive particles. Okay, so n0 here defined 1000. Now lambda equal to, let's say, 0.1. That means it have 10% chance or 10% probability to for decay. Oh, it's 0.1. Okay, then steps equal to, let's say, 100 times. First we will do for 100 times, then we will increase that, and then we will see how the step size affect the Monte Carlo simulation. Now I need an array to store the Monte Carlo result. So for this, decay, suppose Monte Carlo equal to, I have to assign an array. So np dot zeros steps. Okay, done. So now n equal to n0, and here we will use the for loop. So for t in range steps. Okay, so for Monte Carlo simulation, decayed equal to np dot sum. I want to count how many particles are decayed. So np dot sum, which is generated randomly. So np dot random dot rand random from number of n. Okay, for n is n equal to n0, the initial values. Okay, which is less than lambda. Sorry, again, uh, lambda. Okay, that is lambda is 0.1, right? Okay, so now we will minus these decayed atoms from our initial value. So n equal to n minus, sorry, spelling mistake and silly mistake. Okay, so n equal to n minus decayed. Okay, so decayed. Now this is decay. I have to store this data to Monte Carlo decay, which I already assigned this one. So dkm is equal to mc, which is a function of t, mc t capital N, right? Okay, so now it's time for plotting. So exit from for loop and plot sorry, plt, again plt dot plot np dot arrange steps. Okay, decay mc Monte Carlo simulation, I have to put a label. So lavel. Okay, so Monte Carlo simulation. Okay, that Monte Carlo simulation is for leveling, and I want to plot this into green. I have to put it in double comma. Yes, and I want a marker. So marker equal to O, sorry, O, yes, and at last marker size equal to 3. Okay, nicely done. Let's run it first, then we will see the mistakes. Okay, so invalid syntax lambda. Okay, okay, understand. So just lmbda, let's do this. Again there is some problem. N is not defined. Aha, again I have done this mistake. It's capital N. Again some problem is came. Oh, again and again this silly mistake. So matplotlib dot pyplot. Now it will work. Please work. Done. Nicely done. So now it's time to organize things for better understanding. So start from title. So plot dot plt dot title sorry, if of radioactive decay, then lambda. So here I used simple latex. It's very easy in Google Colab. Then plt dot x label equal to sorry, bracket में time, then plt dot y label remaining particles ठीक है. Okay, then plt legend. This is the very important line, legend. Hope it will work. Then plt dot grid and true. I always prefer grid. So now run it. We'll see. So it is the Monte Carlo simulation result. Okay, it looks like exponential decay curve. So now what we are going to do, we will analytically plot the decay curve, assuming that exponential decay curve, which is n equal to n0 exponential e to the power minus lambda t. Okay, and we will see how much differ it is from the exponential decay, and how this steps, or that Monte Carlo simulation steps is affecting these results. So for this, let's start from there. So here I have to put decay exact. I means the exact defining that curve analytical equation. Decay exact equal to np dot zeros. Okay, steps. Okay, done. Now this part is for Monte Carlo simulation. So underlying this, I have to put that exact equation solution. That is decay exact. Just copied it. Yes, exact, which is a function of t equal to n n0 n0 into np dot exponential bracket में minus lmbda lambda into t. That's it. And for plotting, I have to again write the same thing for exact curve, plt dot plot. Okay, so np dot arrange step. So I'm just copy pasting it. I'm very much afraid for a spelling mistake. Let me tell you. Decay exact. Okay, along the y-axis I want this. Okay, then label exponential decay, or exact exponential decay, color equal to color red, color equal to red, and then line style equal to this one, and underline this, sorry, underline this. Okay, so here I add the decay exact. Okay, then I add the decay exact t n0 in n0 into exponential minus lambda t lmbda. This spelling is correct. Lmbda. Okay, okay, done. Nicely done, I think. Then plt plot exponential decay colored, and okay. So here our green line is the results of our Monte Carlo simulation. Okay, so now run it. So you can see That red one is our calculated line, and this dotted red lines comes from this exponential decay curve, and that green lines is our Monte Carlo simulation data. So now I am increasing the step size, let's say 500. So if I run it, see, see, nicely matched. Okay, so if I increase 500 to, let's say, 1000. Okay. So what it actually shows that when we increase our data samples, random data samples, so then the result is approaching the exact exponential decay curve. So finally we can say, so this randomness, this random sampling has a pattern, and the pattern is exponential decay equation, which is n equal to n0 e to the power minus lambda t. Okay, okay, so that's it. So if you like this video, like, share, subscribe.